The theorem statement is the language accepted by finite automata is regular language. So any language that is being accepted by finite automata, that language is called as regular language. So that means finite automata to regular expression. So according to this theorem, see the same statement can be defined in another way also. If a language L is regular, then there is a regular expression to describe, that is L equal to L of M for some finite automaton. Then there is a regular expression R such that L equal to L of R. That means the language L equal to, so the regular expression obtained for accepting the language, that is denoted by L of R. So for any given finite automaton, so we can describe a regular expression. That regular expression, so being generated or accepted from the given language. So finally, whatever the regular expression we will obtain from the given finite automata. Then coming to procedure. So here we will use one of the theorem for conversion of a finite automaton to regular expression. So in Kleen's theorem part 2, so the theorem name is called as Arden's theorem. So Arden's is the name of the scientist. The theorem statement is, so let us take P, Q and R be regular expressions. So then the relationship among the three regular expressions are denoted by the expression R equal to Q plus RP. So whenever the regular expression is in this form, then this regular expression has a unique solution which is denoted by R equal to QP closure. So any regular expression is in this form, R equal to Q plus RP. Here you can see it is in the form of R1 plus R2. So but in the second part after plus, or you can change the order also, no problem. So R should be common in both left hand side and right hand side. So after plus or before plus, followed by some expression. So whenever the expression will be in this form, then you can write its solution as R equal to, the left hand side expression remains same. Then Q as it is, you can take Q. So then you can take closure of P. So this is the solution of the expression R equal to Q plus RP according to Arden's theorem. So in this conversion, we will use the same expression and equivalent solution will be used for generating regular expressions for any given finite automata. Now let us see the steps in the Arden's theorem. So in Arden's method, first we will set up set of equations for each and every state. So for the given automaton, according to Arden's theorem procedure, so we have to set up set of equations for each state. So how to write the equations? Here you can see. For each state, an equation can be written by considering all the incoming state transitions followed by the input symbol. So from a state, let us say Q naught, what are its incoming transitions? You can take all incoming transitions, state followed by its input symbol. Like that, we have to generate equations for each and every state. Now for initial state equation, so we can add one extra symbol which is null denoted by epsilon or lambda only for initial state equation. Then the solution is, so once equations are generated for each and every state, then what is the solution? Which equation you have to solve? So in the given finite automaton, whatever the final state, you can solve that final state equation. So the solution is obtained by solving the final state equation. Then suppose if we have more than one final state exists, then how to find the solution? Find out all final state solutions. Finally, you can take the union of all the final state equation solutions. So these are all the steps we have to follow in Arden's theorem. For any given finite automaton, whenever if you want to construct its equivalent regular expression, first we have what we have to do, we have to write equations for all the states of the finite automaton. For initial state equation, you can add epsilon or null symbol as extra. Then the solution of automaton is by solving the final state equations. So if more than one final state exists, then the solution is union of all the final state equations. So now, how to solve the equations? The process is very simple. Like in our mathematics. So in mathematics, whatever the procedure we followed, so for solving, so you can use the same method we have to use simply by using substitution. So in final state, whatever the unknown values, first we have to find out those unknown values, then you can substitute in the final state equation, then that is the solution. Now let us take one example. Here you can see, construct a regular expression for the given finite automaton. Here the automaton is consisting of two states, Q0 and Q1. The inputs are A, B. Now with this, let us see how to solve this problem. So lively we will demonstrate. So for any given problem, initially what you have to do, write the equations for each and every state as per the procedure defined. So first what you have to do, set up equations for all states of given finite automaton. So now let us take Q0 state. So the equations can be written as, first take the state, then you can use equal, Q0 equal to. So incoming states of Q0 state, any transition on any input, whenever it is coming to that state, only that state you can write. So Q0 on input A, it is coming back to Q0 itself. But Q0 on B, it is going to other state, not coming to same state. So therefore, only you can take incoming state. So what is the state here? Q0. Then on which input it is coming to Q0 itself, on input A. So therefore, you can take Q0 A. So here Q0 is initial or start state. Therefore, for initial state, you can add epsilon or lambda. So this we can make it as equation 1. So careful, you can listen. For initial state equation, you have to add epsilon or lambda. So how to write the equation? For the state, whatever the state you are writing equation, that state equal to. So on which input the transition is coming to the same state. So on input A, so the transition is coming to Q0 itself. So here you can write state followed by the input symbol. So then plus null is added because Q0 is the initial or start state. So here Q0 is initial state. So we have added epsilon or null to this state. Then coming to next second state. So second state equation you can see Q1 is the second state equal to. So now for Q1, what are the incoming transitions? Here you can see Q1 on A, it is going to Q1 itself. So this is incoming. Then Q1 on B, so again it is going to Q1 itself. Then from Q0 on B, so one incoming transition is there, it is coming to Q1. So therefore here total 3 transitions are there. First you can write one by one. First you can take Q0. So from Q0 transition coming to Q1, that is incoming transition. What is its input now? B. So this is Q0 on B, it is coming to Q1. Then plus, then what are the other states? Q1 on input A, it is coming to Q1 itself. Plus then Q1 on B also, it is coming to Q1 itself. So here no need to add epsilon or lambda. Why? Because Q1 is not initial state. So this you can make it as the second equation. So now here you can see, so what is the solution? So which equation we have to solve? Just now we mentioned in the procedure. So whichever the state is final state. So here Q1 is the final state. So here Q1 is final state. So therefore we have to solve Q1 equation. So that means we need to solve this one, Q1 equal to Q naught B plus Q1A plus Q1B using Arden's theorem. So here you can see first here Q1 two times it is there, but here Q naught is there. Q naught we don't know. So first we need to solve Q naught equation. Once Q naught value is obtained, that you can substitute in Q1 equation. Then you can simplify Q1 using Arden's theorem. So finally, we will obtain the equivalent regular expression. So here you can observe, so the final regular expression is combination of only the input symbols followed by the recursive definition rules only. Recursive definition rules. Now states won't be included in the regular expression. Now you can see first we need to solve Q naught. So therefore, one implies first you can take Q naught equal to Q naught A plus epsilon. Here you can see you can apply Arden's theorem by taking, let us take this as R equal to, so let us assume this as Q. Now this is R, then this is P. So R equal to Q plus RP or R equal to RP plus Q, whatever, no problem. So now by applying Arden's theorem, so then here you can see. So by Arden's theorem, so what is the solution? By Arden's theorem, R equal to Q plus RP has a unique solution. So what is the solution? R equal to QP closure has a unique solution. R equal to QP closure. Now substitute R, QP values from the above equation. Now one implies what is R here? R equal to Q naught equal to, then what is Q here? Q is epsilon. Then what is P here? That is input symbol A. So A closure. So that implies now epsilon R or R epsilon equal to, you will get R only according to, so one of the identity of regular expressions or algebraic class. So let us name it as equation 3. Now we obtain direct Q naught value. Now substitute this Q naught value. So in the equation 2, so therefore that step you can write down. So now substitute Q naught from equation 3 in Q2 equation. So that is Q2 equation is 2. Therefore 2 implies, first you can write down the second equation, Q naught B, Q1 equal to Q naught B plus Q1A plus Q1B. So the equation 2 is, so Q1 equal to Q naught B plus Q1A plus Q1B. Now substitute Q naught value from equation 3. So what is Q naught value? A closure. So therefore Q1 equal to, what is Q naught value? A closure. The B remains same plus Q1A plus Q1B. Now again you can simplify this one by applying Arden's theorem. Here you can see Q1 is common in both Q1A plus Q1B. You can take Q1 common. Now this will becomes Q1 equal to A closure B plus, now you can take Q1 common. Now this will become A plus B. Again apply Arden's theorem. Let us assume this is R. So R equal to, again this is R, then this is B, now this is Q. So now R equal to Q plus RP. Again by Arden's theorem, R equal to Q plus RP has a unique solution. So unique solution, what is that unique solution? R equal to QP closure has unique solution. So that is R equal to QP closure. So now this will becomes now 2 implies. So therefore R equal to Q1 equal to what is Q here? So Q is nothing but A closure B. A closure B. Then what is P here within parenthesis after R? A plus B. Now this will becomes A plus B, its whole closure. So therefore Q1 equal to A closure B concatenation with A plus B whole closure. Now you can see this is the solution of the final state equation. So is the required regular expression, is the required regular expression for the given finite automaton. That's all. This is the solution of the final state equation. So now this is the equivalent regular expression for the given finite automaton. So you can recall once. So what we did here, very simple. So the given finite automaton Q0 is the initial state. Now Q1 is the final state. So now as per Arden's theorem, the solution of this problem is we have to solve the final state equation. Here we have only one final state equation. Simply we can solve this final state. That's enough. Suppose if we have more than one final state, so at that time what you have to do, you can solve all final state equations. Then you can take union of all the final state solutions. So now here only one final state we have. So we need to solve only that equation. Now for setting up equations for all the states, the rules are for initial state, you can take epsilon or lambda as the additional symbol. For remaining states, as it is, you can take all the incoming transitions. How to write the equations? The incoming state followed by its input symbol. Like that you have to write. Now for Q0 state here you can see Q0 equal to what are the incoming transitions on input A. There is one transition coming to Q0 itself. Therefore, the Q0 equation equal to Q0 equal to Q0 A. So Q0 is the initial state. That's why here we have to add epsilon or null. So therefore, plus epsilon is added. Let us assume it as equation 1. Then coming to equation 1 Q1. For Q1, see what are the incoming states followed by the transitions. From Q0 on B, one transition is coming. Then Q1 on A and Q1 on B. So for self loop, you can take incoming same itself will be the incoming transitions. So therefore for Q1 we have 3 transitions. So can be written as Q1 equal to first Q0 B plus Q1A plus Q1B. So whenever you are writing the equations, first you have to write the incoming state followed by its input symbol. That is the order we have to follow. Now Q1 equal to Q0B plus Q1A plus Q1B. Let us assume it as equation 2. Now our target is we have to solve the final state equation. Here what is the final state equation? Q1 is the final state. So we need to solve Q1. So therefore to solve Q1 equation, here Q0 is there. First you need to find Q0 value. That value you can substitute here. Then the equation is in terms of Q1 only. Then you can take Q1 common. Then you can apply Arden's theorem wherever it is applicable. Then you can simplify. So now to find Q0 value, first we have to solve equation 1. So therefore Q0 1 implies Q0 equal to Q0A plus epsilon. So directly it is in the form of Arden's theorem. So by assuming what is R, what is P, what is Q in both left hand side and right hand side, by equating to Arden's theorem, now this will becomes R equal to Rp plus Q or R equal to Q plus Rp, whatever the same. By Arden's theorem, R equal to Q plus Rp has a unique solution, that is R equal to Qp closure. Now you can substitute RQP values from the above equation 1. Now this will become Q0 equal to epsilon A closure. So that is Q is epsilon here. Now P is A. So therefore epsilon A closure. So now according to algebraic laws of regular expressions, we have one identity epsilon or R closure or R epsilon or R closure epsilon. So equal to, you will get R only. So therefore, according to that identity, here epsilon A closer, you will get A closer only. Therefore, Q naught equal to A closer. So now Q naught value is obtained here. Now this value you can substitute in our target equation, that is Q1 equation. So which can be named as equation 2. So now substitute Q naught from where? We assume this as equation 3. Q naught value from equation 3 in Q2 equation. What is that equation number? In bracket we mentioned 2, equation 2. So therefore 2 implies, so you can take the Q1 equal to Q naught B plus Q1A plus Q1B. So now you can substitute Q naught value from the above equation 3. So that is A closer. Therefore Q1 equal to A closer B plus Q1A plus Q1B. Now Q naught is eliminated in equation 2. So now the equation is combination of Q1 and some expressions only. So now you can take Q1 in the right hand side. So therefore the equation becomes Q1 equal to A closer B plus Q1 is taken common. Now after taking Q1 as common, so remaining are A plus B. So now again it is in the form of Arden's theorem. So by equating to Arden's theorem, let us take Q1 as R in the left hand side, then right hand side A closer B, make it as Q, then plus after plus Q1 is again R, then remaining part you can make it as P. Now it is in the form of R equal to Q plus RP. Directly it is in the form of Arden's theorem. So then it has a unique solution, that is R equal to QP closer. So now by substituting in the Arden's solution, therefore R means Q1. Q1 equal to, Q means A closer B. A closer B, then P closer. What is the P value? A plus B. Closer means so its whole closer. So A plus B whole closer. So therefore Q1 equal to A closer B, A plus B whole closer. Now you can see in a Q1 equation, it does not contain any states in the right hand side. So it is in the combination of the input symbols A, B and with the regular recursive definition parameters only. So it contains closure, parenthesis, then union, then concatenation, combination of the recursive definition rules only. Therefore, this is the final required regular expression for the given finite automata. So this is the solution.